Welcome to the Explainer. Today, we're taking a look back at the evolution of network traffic. We're going to compare the absolute chaotic shouting of early hardware to the incredibly precise direct delivery systems we rely on today. Let's just jump right in and see exactly how computer networks evolved to handle the massive amounts of data we push around every single day, just by fundamentally changing how they talk to each other.
So we all know early networks were, well, chaotic. But to really wrap your head around it, I want you to picture a loud, super busy office environment. Imagine you're standing right in the middle of this large office, and you need to pass a sensitive message, maybe a secret, to your colleague, John. But instead of just walking over to John's desk and telling him directly, the rules of this particular office dictate that you have to grab a giant megaphone and shout your message to literally every single person in the room. Sounds incredibly inefficient, right? No way you'd actually work like that. Well, for a long time, this was exactly how early computer networks functioned.
That megaphone in our office scenario, that perfectly represents the classic network hub. Now, as a basic networking device used to connect multiple computers together, you probably already know it operates at layer 1 of the OSI model, the physical layer. And what that really means is the hub has absolutely no intelligence. None. Zero. It acts as a totally dumb repeater. It receives an incoming electrical signal on one of its ports, and its only response is to blindly shout it out everywhere, to every other connected port, completely regardless of who the data was actually meant for. It's got no memory, no internal address book, and absolutely no ability to make decisions.
Okay, let's dive into this megaphone analogy a bit more, because it perfectly captures a major networking problem called flooding. When you shout that message for John, every single person in the office has to drop what they're doing and listen. They process the first few words, and 99% of them go, "Oh right, this message isn't for me," and then they go back to work. Out of all that massive disruption, only John actually takes the info and does something with it. In a network setting, when a hub receives a message and has literally no idea where to send it, it just screams it at every connected device and crosses its fingers that the right person is listening. That unnecessary shouting, that is network flooding.
And the real-world consequences of this flooding are pretty severe, especially as you start adding more computers to the mix. First up, you've got massively wasted bandwidth. Your network cables are just bogged down carrying data that almost nobody needs. Second, wasted CPU power. Just like those distracted office workers, every single machine on the network has to pause its own processing to inspect every passing data packet, only to just throw it away. And third, and this is a big one, there's a huge security risk. Because every conversation is entirely public, a nosy device can just sit there on the network with a packet analyzer and read all the traffic passing through the hub. There's absolutely zero isolation.
But wait, flooding isn't even the only issue. As you likely remember, all devices connected to a hub share the exact same collision domain. Because they all share the same electrical medium, think of it as essentially one single wire. If two devices try to transmit data at the exact same time, those electrical signals literally crash into each other. Boom! Both transmissions are completely destroyed and corrupted.
Think of this collision domain kind of like a group of friends sharing a single walkie-talkie channel. Only one person can talk at a time, right? If two people press the button and talk simultaneously, their voices overlap and become entirely garbled. That is a collision. When that happens, everyone has to back off, wait a random amount of time, and try again. On a network hub, devices use the CSMA/CD protocol to detect these collisions and retry. But as you add more devices, well, imagine 10 people fighting to speak on one walkie-talkie channel. Performance just degrades exponentially. What works passably for 2 devices becomes practically unusable with 20.
This walkie-talkie limitation brings us to another hard physical reality of hubs. They only support half-duplex communication. You can either send data or you can receive data, but you can never ever do both at the same time. And this isn't some design flaw, it's simply a consequence of physics. If 2 electrical signals travel down the exact same wire in opposite directions, they corrupt each other. Contrast this with a modern phone call, which is full duplex. On a phone call, both people can talk and listen simultaneously because they have dedicated lines with absolutely no interference. So, taking stock here, we have severe bandwidth waste, CPU drain, massive security flaws, constant data collisions, and the physical limitations of half-duplex communication. The hub was, to put it mildly, an incredibly chaotic foundation for a network. The big question became, how do we stop the shouting? How do we fix all of this without completely reinventing the entire concept of a computer network?
Enter the network switch. The switch is really the hero of our explainer. Unlike the chaotic, blindly shouting hub, a switch operates at layer 2, the data link layer. which means it actually has some intelligence. Instead of one shared wire, a switch gives every single connected device its own dedicated connection. And most importantly, it maintains a MAC address table. Think of this as a highly efficient internal address book that maps every single connected device directly to its specific port. When data arrives, the switch looks up the exact address and sends the data only to that specific port. Everyone else on the network is completely undisturbed. Organized relief, finally.
Now, what's really interesting about this slide is how the switch actually builds that address book. It learns over time. Let's bring in a postman analogy. A hub is like a terrible postman who knocks on every single door on the street every single day to deliver one letter, no matter how many years he's been working the route. A switch, though, that's a smart postman. On his very first day, when his address book is empty, sure, he might have to knock on every door to find the right house. In networking terms, the switch will flood that very first frame of data. But once the device responds, the switch records that address, it learns on day one, and from that exact moment on, it delivers directly to the correct door. It never makes the flooding mistake with that device again.
And this brilliantly illustrates the complete superiority of direct delivery. When you stack them up side by side, you can clearly see how the switch solves every single problem the hub created. Moving from layer 1 up to layer 2 intelligence means traffic goes direct instead of broadcasting everywhere. Because each port has its own dedicated connection, collisions literally disappear. Every port is its own completely isolated collision domain. This also unlocks full duplex communication where devices can send and receive simultaneously. Security is inherently improved because traffic is isolated and scalability entirely restored. Adding more devices no longer brings the whole system crashing to a halt. Because switches essentially solved all of these deeply frustrating network problems, and because the actual manufacturing costs between a hub and a switch eventually dropped to near zero, there is absolutely no practical reason to use a hub in any modern network. They've been completely abandoned. Today, hubs are considered pure legacy hardware. You won't find them running in any serious environment. Really, they survive today strictly as a teaching tool. They are the absolute perfect textbook illustration of what not to do when designing a system for efficient communication. By shifting from blind broadcasting to intelligent, direct delivery, network switches literally pave the way for the high-speed, secure internet we all enjoy today. It's a massive leap forward. But it really makes you think about efficiency in other areas of tech, doesn't it? As we leave the digital shouting behind us, I want to leave you with this thought. What other inefficient megaphones or legacy technologies might still be secretly broadcasting in your daily life, just waiting around for a smarter upgrade? Something to think about. Thanks so much for joining me on this explainer, and I'll catch you next time.